So it's Saturday morning and it's raining, and so I can't go on a bike ride, so I thought, what could I do constructive? And I thought, hey, why don't I put together a little quick example for my calculus students about a function, its derivative, its second derivative, and the relationship between functions, mins, maxes, inflection points, and critical values, and all that stuff that we've been doing for the last couple of days. So that's what I decided to do. Okay, now here I have a derivative. This is a derivative function, and I've graphed the derivative function. And in fact, let me write it out here in function speak instead of computer speak, so it's a little easier to see. 2x cubed minus 8x squared plus 8x minus 1 all over x minus 2 squared. So there's our derivative. That's f prime. Okay? And here's the graph of that derivative right here. Okay, now you notice critical values are when the function or when the derivative is equal to 0. Okay, this is going to be a little bit hard to figure out where this is equal to 0. The easiest way to do it is with the calculator. If you have to do it by hand, it's going to be tough because it doesn't factor very well. You can see, though, that there's also a critical value when x is equal to 2. Because when x is equal to 2, the denominator is 0 and the derivative doesn't exist. And that's also a place where we have critical values. So it looks like, based on the graph, I've got 3 places here where I know I have critical values of 0, right here. I'm sorry, derivatives of 0, here and here and here. Okay? And then also at the asymptote, so x equals 2, there's a critical value. Take a look at this first critical value, right here, whatever that x value happens to be. Do you notice how the derivative is negative on one side and positive on the other side? What that says to me is that we have a function that is decreasing in this part and increasing in this part because of the sign of the derivative, which means this place, this location at x, has to be what? That's right, a minimum. So I'm going to draw a graph that has a minimum right there. There's a minimum. Okay, and I went out a little bit too far, so I'm going to get rid of that. Okay, so there's a minimum. Over here, what's this have to be? Function increases in this region, decreases in that region. We have to have a maximum here. And that's kind of what the function's starting to do. It's actually going to go up, it's going to max out, and then it's going to come down. What happens to the function over here? It's decreasing, decreasing faster, 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 faster. And look what happens. We end up falling off like that. Okay, now I'm going to come back to what we do here in just a second. On this side, this has to be another minimum of the function because the derivative is negative on the left, so the function's falling. Then the derivative is positive on the right, so the function's rising again. And see how steep this derivative is? That means the value over here is very negative in a very small space of x. So what we have here is a function that really is quite steep, like this. And then it goes up. Something like that. Okay? So, min, max, and a min. Cool, huh? The asymptote. Oh. Wait a minute. I just realized something. No, that's right. I was right. Duh. Right here, the function's falling, so we're coming from the top down like that. Okay. Normally, this is going to have to be an asymptote because there's no way for the function to join each other when this side's going down and this side's going up. So we have to have an asymptote right here too. And then this is going to continue up like this, and this is going to continue up like that. Okay, now the next problem we have is we got to find the inflection points. Okay, that's actually going to be pretty easy. Inflection points happen when the derivative has a max or a min. Okay? So in other words, inflection points happen when the derivative is equal to 0, and on one side of the 0 the derivative is increasing, and on the other side of the 0 the derivative is decreasing. Does that make sense? Let me show you. Let's call that a point. This is left of x, this is right of x. If we have an inflection point, what that means is that f prime has to be 0 right here, has to be negative on the left and positive on the right, or the other way around, positive on the right, negative on the left. Okay? And that's one of the things that we saw yesterday in class. Does that happen here? Sure does. The derivative comes up, tops out right here, which means the derivative increases, then decreases. So what does that say about the function? The function has to be concave up on this side because the derivative is positive. Try it again. The derivative of the derivative is positive. Derivative is increasing. Here the derivative is decreasing, so this has to be concave down. Where this maximum occurs on the derivative is our inflection point. So we actually have an inflection point here, concave up, concave down. And then what about over here? Does the derivative ever top out? It doesn't look like it. Now maybe it would top out somewhere over here someplace, and we can probably zoom back and check that out in a bit. Okay? But see, there's no maxes or mins of the derivative, so that means there are no critical values of the derivative, and there are no changes in signs of the second derivative. And so there are no changes in concavity. So right here, just looking at the graph, you can tell it's concave up. And so there are no inflection points on this side either. Okay, now, I'm going to go ahead and just graph the function this came from, and we'll see how close we got. Okay, the red line, this line right here, this line is the function it came from, and this is the function right here. Okay, so you can see we actually got pretty close. We have a minimum right here, we have a maximum here, we have an inflection point where the concavity changes from concave up to concave down, right there. Okay, and the inflection points are harder to detect. You know, they're not obvious like mins and maxes. But what about over here? What happened over here? Well, here's what I suspect. I suspect that this graph does exist. It's just way up here. It's farther up. So what I can do is I'm going to go ahead and erase all these annotations, and then I'm going to zoom out the graph, and let's see if we can find it. So let me go over here and erase all the work that I did. Okay, and then we'll go ahead and let's zoom this back, and let's see, there it is. There's the function, and that's indeed what it does. It comes down really fast and goes up really fast. And it looks like this derivative never comes back and wraps around on itself like that. So the derivative, if it were to go up and then at some point wrap around, then that would change this curve, but it's not going to do that. You can take a look at the curve and see it's a second degree, or it's a second degree? Yeah, it's a second degree curve. So it's actually, it looks like it's a parabola with an asymptote in the middle of it. So anyway, well, we're going to talk about that in a bit. All right, there you go. Have a good weekend.